Yes, Pak.
Okay. So we quickly review what we are discussing yesterday, what we were discussing yesterday. Okay. It's about electromagnetic waves, the waves that can propagate without medium. Yeah. Okay. So this is basically is the crowning achievement of James Clerk Maxwell, that he can predict the wave, called electromagnetic wave, that can propagate without the medium. This is the opposite, from the wave mechanic theory, because the wave mechanic theory, the wave can only propagate with medium. So, for example, the sound and for string waves, that's the example. Okay, as we have discussed yesterday, this is the spectrum of the electromagnetic waves. Okay, so this is the long wave or with low frequency. This is the short wave, and this is with higher frequency. Okay. So basically, this is the visible light. Okay. So basically, we have, for example, the phenomenon, physical phenomenon like wave, for example. So the wave, the light. Okay, the light, as we know, can be modeled. Can be explained by electromagnetic wave theory, okay, such as, for example, we could explain the phenomenon of interference and diffraction of light, using this electromagnetic wave. So it means that the light have wave property. So in this case, this is electromagnetic waves. Okay. So this is the wave length, and this is the frequency below. Okay. So this is basically for maritime and aeronautical uses. This frequency, this is for radio, and also this is for maritime and mobile radio, for example. This is FM radio. AM, it means that amplitude modulation. FM, it means that frequency modulation. You will study it maybe in the next level. There is a special course on wave, I think, in your faculty. There's also TV channel, and also some of this will be used, for example, for maritime, band, and mobile radio also. Okay. So if, for example, X-ray and gamma rays, this is also electromagnetic waves, but the particle properties in this case is dominant for X-ray and gamma rays. Okay. So it means that if we have this higher frequency, the probability of the light have particle properties is bigger than the lower frequency. Okay. So on the left hand side, this one. So this is wave properties dominant of the light. And this is also between them. Wave can sometimes also wave properties, sometimes also particle properties. But in this case, on the right hand side, the light have a dominant in particle properties. Okay. So we have discussed about this, I think. Okay. So how to generate, how to produce electromagnetic waves, basically coming from the oscillator, we call it LC oscillator, and we have this electromotive force, EMF, AC EMF. So somehow using this RLC circuit, we get somehow this resonant frequency, okay? So we have this frequency, and this is also using transformer. We could transmit this wave, yeah, this oscillation, yeah, through the antenna, okay, as electric dipole. So the antenna will send, yeah, this wave, yeah, outside the source, okay. So this is how to generate the electromagnetic waves, okay, using LC oscillator, okay, at the angular frequency like this, which is the resonant frequency. Okay, as we have discussed yesterday, we have in electromagnetic waves is a vector wave function. It means that we have electric component and magnetic component, okay. This is the greatest magnitude. For example, this E becomes smaller, also B, and then becomes 0. And then they turn different phase, okay? Pi different phase, 180 degrees, become minus, 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 and 0, and then again. So let me show you the picture. So the picture in this case is like this, okay? So we also have discussed about this C here. This C is the speed of the wave in the vacuum, okay? And also we assume that the electric field, electromagnetic field component of the wave, yeah, of the electromagnetic waves, and also B have the same sinusoidal function. Okay, this EM and DM denote the amplitudes of the fields, okay? Omega is the angular frequency, and K is the angular wave number. So the connection, the relation, sorry, between EM and BM, yeah, EM over BM, the ratio EM over BM is equal to C, okay, which is C is the speed of the wave in the vacuum. So this is the wave, okay. We have electric component, sorry, magnetic component B, yeah, at the z-axis, and also the electric component on y-axis, okay. And they propagate along this x-axis. So this is about, yeah, almost the exact value of the speed of light, yeah, in the vacuum, we have discussed, I think we have discussed this one, okay. So, what is it again? Okay, this is only the derivation. Yeah. How do we get the ratio between E and B equals C? Okay. Okay, so also we have discussed about the pointing factor, which is related to how much energy that can be transported. Yeah, sorry, that is transported by the waves. Okay, the factor finding it describe the flow, the energy flow of the electromagnetic waves. Okay, and as we saw, so as we see in the picture, for example, this one. Which one? This one, okay. This E cross B is equal to S, okay. So the vector of the S is parallel to the propagation direction of the waves, okay. Okay, this is the S here is the energy flow of the electromagnetic field. In this case, this S equal to E cross B over mu 0. Okay, so the magnitude of S, yeah, is the power of the area. Okay, so the power over area, we call it the intensity of the waves. So basically, intensity in this case, because the electromagnetic waves describe the light, so it means that we have the bright. This intensity is related to the bright level, yeah, of the light. Okay, while in the sound is the loudness level. This intensity related. Okay, the loudness level in the sound in this case is the bright level. Okay, so we see that because E and B is proportional, yeah. So it should be this, the magnitude of S is proportional to the S square, to the E square. Okay. So this, we basically get that ERMS is equal to EM over square root 2. Okay. Any question here? Okay, this is the power here. Okay, this is the book from Haile Resnick, yeah, and Gene Walker. You already know. And so we have also the radiation pressure. Yeah. For example, this is related to the momentum. Yeah. P equals to U over C. So the momentum change, delta P, is proportional to the change of the energy, internal energy. Okay. This is the total absorption. And this is for the total reflection along the path. Yeah. This twice delta U over C. Okay. Any question? Okay. So the average force in this case is delta P over delta P. Okay. So we get that, yeah, using this definition. So we get that this F is proportional equal to E times A over C, where I is the intensity while A is the area. Okay. So this is for total absorption, and this is the total refraction. Okay. This 2 here, the number 2 here, where does it come from? Muhammad Faza. Hello.
Hello, sir.
Yes. Where these 2 come from?
The 2
total reflection.
I think it's from the F equals to yang rumus di atas, Pak, to I per to IA per C. Apa dari situ ya?
This one.
Sir.
Yes. 33. This
33.
One.
Yes, sir. I think it's from
okay.
there.
And I ask again, where these 2 come from?
Is it from that delta P, sir? Because it's written as 2IA. Is it from there?
Sorry?
Is it from the delta P equals to
delta
IA?
P.
Itu dekatnya, Pak, itu kiri sedikit. Apakah dari situ ya?
Yang mana ya delta P?
Itu tepat di tadi. Aduh. Dekat kursor Bapak tadi.
This one.
Yeah, I think is it from there, sir?
Yes, of course. The question is where this number 2 come from? Twice. Because the total absorption we have only I. Okay, but total.
Is it because reflection, sir?
Sorry,
because it's going twice, like back and forth. Is it because like that, sir?
Yeah, exactly. Yeah. Because total absorption we have only one direction. But total reflection, we have two directions, incident and reflection. Okay, we will discuss it later to make it clear. Okay, so today we will discuss about polarization. Okay, so as I mentioned before, for example, polarization is related to the direction of oscillation of the electromagnetic waves. For example, E, which direction related to the oscillation direction of the waves? The oscillation direction. Hello, hello, hello. Let me ask. Bagas.
Ya, halo Pak.
Yeah. Which one is the direction of oscillation direction?
Would it be perpendicular to
Sorry?
the perpendicular?
Which axis?
Oh, Y.
Y, okay, good. So the direction of this, the direction of oscillation, yeah, okay, it's Y, okay, this X, yeah, is the propagation direction, okay. So for example, this one, okay, this wave, okay, we have simply look from behind, okay, this is E, yeah, and also this is E, yeah? B is in the z-axis, okay. But in this case, we just consider only E. Yeah? So we could also consider B, but it has the same properties, yeah, as E. Okay. So let's just consider this electric field. Yeah? So the electric component of the electromagnetic waves. Okay. So in this case, yeah, for these waves, okay, the oscillation direction only on y-axis, okay, plus and minus. It say that the direction of oscillation, the direction of oscillation of the waves is fixed in this case, okay. Fixed, I means that only on y-axis, okay. This is called a polarized light or polarized electromagnetic field. So the polarization direction in this case is y-axis. Is that clear? Hello? Is it clear? Is there anybody cannot understand what I mean or not completely understand? Hello, hello? Is it clear? Anyone? Hello, hello?
Clear, sir?
Okay. So this is the polarized electromagnetic waves, okay? Because the oscillation direction only on y-axis. So for example, this is the example unpolarized axis, unpolarized wave, electromagnetic waves or light, okay? So somehow they these oscillate everywhere, okay? Everywhere on the circle, the direction, okay? So this is unpolarized light, okay? Because this is so complicated. If we draw, okay, we just symbolize that the unpolarized light, we just write like this only on y-axis and z-axis. Okay. Is that clear? Hello. So this means this is only symbolized. Okay. So in reality, this one. Okay. Okay. I hope you understand. So this is, for example, yeah, about the symbol what I mean before. So this is, for example, unpolarized light, okay? And there is, we call it polarizing sheet, yeah, made from a material that can polarize the light or the electromagnetic waves, okay? So if the incident light, which is unpolarized, passing through this material, and then they become polarized light. Yeah. Okay. So you see that in this case, okay, we have vertical. So the polarizing sheet, okay, we set that such that if the polarized light will be vertical, okay, will be vertical. I hope you understand what I mean. So what is the intensity of the polarized light? Okay, there is a formulation by Malus. Yeah, Malus. Malus is the name of the person who derived this formulation 33 minus 38. This the equation 33, 38. Okay, this is called the Malus law. Okay, somehow, if we have, for example, I0 is the initial intensity of the light or the electromagnetic waves, I is the intensity after the light passing through the polarizing sheet. Okay. And cos theta is related to the angle between the unpolarized light, okay, the amplitude, and the sheet, yeah, this vertical sheet, okay. In this case, is y-axis, okay. So this is for example, yes, this is unpolarized light or electromagnetic waves, okay. And then this light passing through this P1, which is the polarizing sheet, and this is vertical, okay. And we get that the resulting light or the resulting waves will be vertically polarized, okay. And then if this polarized light, okay, passing through this polarizing sheet, but the polarizing sheet we rotate, for example, theta with respect to the vertical line, okay? And there will be no light or polarized light passing through this polarizing sheet, okay? Is that clear about this picture? I will summarize our lecture today in Indonesia, in Bahasa, ya, before the end of the lecture. Okay? So, okay, yes? Is there any question? Hello?
No question, sir.
Okay, okay. So what this mean about this the advantage of this polarized light, okay? This is the figure 3314. This overlapping polarizing sheet, okay? So, for example, in this first line, yeah, we can see, yeah, about this polarized, the picture behind the polarizing sheet, okay? And if we take the second one, and this become unclear, okay? I mean, become darker, okay? So it means that is the indication that the intensity is become smaller after the light passing through these two polarizing sheets. Okay. So in general, usually we can only see the dark. Okay. But somehow this polarizing direction of the light cannot passing through this polarizing sheet. So this is, you see that this is the vertical, okay? Both vertical, okay? This polarizing sheet. But if I rotate this, the second polarizing sheet, yeah, this is horizontal, then this is become dark, okay? Somehow the polarized light cannot be passed through, yeah, this second polarizing sheet. Okay. Okay. Figure 3315A. Which one? Okay. This one, yeah. A. A should be this one. Okay. This is unpolarized light. This is polarized light. Okay. This is so this is the polarized light. This is vertical, and then we rotate this polarizing sheet by 60. Okay. And there will be this polarization direction is 60 degrees, yeah, from this vertical axis. And then if we rotate again, okay, the emerging light will be polarized horizontally. Okay. Okay, this is the picture. Okay, this is I0, I1, I2, and I3. Okay. So you see that from okay, from this one, okay, this one, yeah. The first sheet is 60 degrees. Okay. Sorry. No. Just a moment. Sorry. This theta one is 0. Okay. Sorry. Okay. Just a moment. Sorry about that. So let us discuss this first. Okay. This is the unpolarized light. Okay. So this unpolarized light. Okay. It will be passing through this vertical polarizing sheet. Okay, they will be emerging of this vertical polarized light is like this. Okay, vertical. Okay. Okay, and this intensity that the emerging intensity of the polarized light, yeah, the vertical polarized light will be 1/2 I0. Okay, so this is, we call it this 1/2 rule. Okay, So it can use on it only when the light reaching a polarizing sheet is unpolarized. Okay, so basically I0 is the intensity of the unpolarized light. Okay, while the vertical polarized light, the intensity is 1/2. Okay, so the malus law is only valid for polarized light. Okay, for unpolarized light, yeah, we only have this this rule, this 1/2 rule. Okay, basically this 1/2 rule, it means that the emerging vertical or horizontal polarized light, okay, is 1/2, yeah, from the unpolarized light, like this, the picture like this. We could also vertical or horizontal. It's the same. So if we have from unpolarized to polarized, the intensity of the polarized light will be this one, I equal to 1/2 I0. Okay, and then the rest, yeah, for the polarized light, we use this malus formulation. Okay, so in this case, for example, the first sheet, okay, the first sheet from this one, okay, because this is unpolarized light, okay, this I1 is, it should be I1 equals to I1 equals to 1/2, yeah, I0. Okay, because this is from unpolarized to polarized. Okay, and then this, the second is I1 reach the polarizing sheet, the second polarizing sheet, with angle 60 degrees. Okay, so it should be I2 here, it should be I2 equals to I1 cos squared 60 degrees. Okay, the third sheet, okay, because this is polarized sheet, okay, I3 because this is horizontal, so it should be from this after 60, okay, this should be 30. Okay, this I3 should be I2 cos squared 30 degrees. Okay, if we insert this equation to this equation, we will get this I3 equal to I1 cos squared 60 degrees cos squared 30 degrees. And we will get the ratio of I3 over I0 is this one, 0.094. Okay. So, is there any question about polarization properties of the light? Any question? No. Okay. We will continue about reflection and refraction. So if you see from this picture, this one is the incident light. This one is the reflective light, light, and the green one is the refractive light. Okay. So we could draw, yeah, the phenomena like this. We have the incident ray, okay, and then this ray is reflected by the waterfront, yeah, water surface, okay. So this is between air and water, okay. So in reflected wave, okay, or light, we have the same angle, okay, theta1 and theta1 prime is equal. Okay, this theta1 equals to theta1 prime. Okay, so this vertical line we call it normal axis. Then We have also refracted ray or refracted light. Yeah, this is theta 2 with respect to this normal axis. Okay, so the composition is quite simple if you already study about this Maxwell equation. So the beautiful thing about this one is the reflection, the theta 1, as I mentioned before, is equal to theta 1 prime. Okay. So basically, if the light refracted by, for example, a medium surface, we will have the same angle, okay, with respect to the normal axis. For example, this one. And then the law of refraction, yeah, satisfying this law. This law we call it Snell's law. Okay, Snell derived it from the principle of extremization. Yeah. The shortest way how to connect 2 points. Yeah, so basically, this using this, we call it optical geometry. Yeah. We consider the light as only the line. Okay, there is no physical properties in the line. Okay, so in the physical optic, yeah, we consider light to be electromagnetic wave. Okay, by the boundary condition, we could derive this Snell's law. We call this Snell's law of refraction. Okay, this n1 and n2 is the dimensionless constant. Yeah, we call it the index of refraction. Okay, this is the table of this index of the refraction. For example, the vacuum exactly equal 1 exactly, and also air at room temperature we have almost 1. Okay, water at 20 degrees 1.33. I think mirror. Is there any mirror or? Okay. Okay, this is the indexes of refraction of some material, okay, some fluids. Yeah. So this is basically for example, if the incident ray or the incident light coming from the same material or the same medium as the refractive, okay, or this is the incident ray or incident light and the refracted ray in the same they both have in the same medium. Okay, this n2 equal to n1. Okay, this n1 is the upper medium, n2 is the below medium. Okay, so like this. For example, if n2 is greater than n1, okay, we have the same refraction law. Okay, theta 1 is always equal to theta 1 prime. This one and also this one. Okay, but the refracted angle or the refracted angle is different. I mean, somehow bend toward the normal axis. Okay. This one. This is for n2 greater than n1. If n2 less than n1, for example, from the glass or the water to the air, okay, they will bend away from the normal, the refractive ray, okay, refracted ray. Okay. Also valid for refractive law and Snell's law. Okay, in general, their index of refraction and of the light in a medium, it's not really a constant, but it depends. For example, it depends on the temperature, for example, and also in this case depend on the wavelength. Okay. That is in general, not really constant. If this this index of refraction depends on lambda, it means that we call it, this is the chromatic dispersion. Okay. This is, for example, if the light were, we have a color, blue and the red, okay? Blue and the red. So the red, usually this refracted angle is greater than refracted angle of the blue, okay? This is from air to the glass, for example, where this N2 is greater than N1. But the other way around, if the incident light, okay, coming from this glass, okay, we have that the refracted light, yeah, for the red is less than blue, the refracted angle. Okay, the blue is always bend more than the red. So this is for the example of chromatic dispersion. Yeah. Somehow we have, at the beginning, we have the white light. White light is the mixed light, yeah? Mix of the colorful light, okay, from white. If this light passing through, reaching this prism, okay, this prism, it will be somehow spirited, yeah, from the red to the blue. Okay. Oke, saya akan simpulkan kuliah kita dalam bahasa. Oke, jadi dalam hal ini kita sudah membahas tentang apa tadi? Is there any question? Halo? Is there any question? Oke, tidak ada. Oke. Jadi kemarin kita membahas tentang apa namanya? Medan elektromagnetik, ya, ini sedikit pengulangan, bahwa intensitas itu terkait dengan daya dibagi dengan luas, ya. Jadi intensitas ini kalau dalam suara itu terkait dengan level, apa istilahnya, keras atau tidak terdengar, terdengar atau tidak terdengar, loudness, ya, berisik atau tidak berisik. Tapi kalau yang intensitas terkait dengan cahaya itu adalah terang atau gelap. Jadi gelap itu yang belakangan, ya, yang destruktif gitu ya. Kalau yang terang itu yang saling menguatkan. Oke, itu terkait dengan intensitas. Dan intensitas ini juga terkait dengan gaya yang diakibatkan, artinya dia punya hubungan antara gaya akibat radiasi dengan intensitas. Seperti ini yang kita gambarkan. Angka 2 di sini itu datang karena yang datang dengan terpantulkan itu ada dua gelombang. Jadi makanya dia ada dua I di sini. Sedangkan dibiaskan atau di refraksi itu cuma satu. Atau yang diserap lah isinya gitu. Nah, jadi cahaya itu secara umum itu adalah bisa dimodelkan dengan menggunakan gelombang elektromagnetik. Dan secara umum, ya, cahaya itu adalah gelombang yang tidak terpolarisasi. Jadi Polarisasi itu gampangnya itu gini. Ini kalau kita lihat.
Assalamualaikum. Waalaikumsalam.
Halo, any question? Ada pertanyaan? Oke, nah jadi kalau seperti ini kita lihat, ini kan arah osilasi ke sumbu Y. Dan ini sifatnya fix gitu ya. Kita hanya meninjau medan listriknya saja. Untuk medan B harusnya sama ya. Karena kan B dengan E itu terhubung. Oke? Jadi kalau E-nya berubah, B-nya juga berubah. Gitu. Jadi ini contohnya. Jadi ini adalah contoh dari medan atau gelombang elektromagnetik yang terpolarisasi secara vertikal. Oke? Ya, sumbu Y-nya itu ke sana. Jadi arah oscilasinya itu fix. Kalau yang dia tidak terpolarisasi, itu gambarnya seperti ini. Oke? Cuma disimbolkan biasanya tuh cuma yang bagian Y dengan Z. Gitu. Untuk memudahkan, karena arah getarnya ke segala arah itu, apalagi ini sambil berputar gitu ya, itu susah gambarnya kan gitu ya, segala arah. Jadi kita cukup gambar yang seperti ini aja. Nah ini contohnya misalkan ini yang cahaya tidak terpolarisasi, dia melewati lembar, ya misalkan lembar untuk yang mempolarisasikan cahaya gitu ya, polarizing sheet. Gitu. Kalau ini vertikal, maka dia akan dapat dia vertikal. Nah, dari sini itu kita dapat hubungan yang disebut namanya hubungan aturan setengah. Ya. Jadi, kalau I0 itu adalah intensitas awal dari cahaya yang tidak terpolarisasi, maka hasil intensitas dari yang terpolarisasi itu adalah 1/2 atau 1/2 maaf, atau setengah dari I0. Ini adalah dari yang tidak terpolarisasi jadi terpolarisasi. Oke? Nah, secara umum kalau dia itu cahaya terpolarisasi itu maka mengikuti persamaan 33/38 ini yang kita sebut namanya hukum malus. Nah, hukum malus ini itu diperoleh dari hasil eksperimen. Oke? Nah, ini sebagai contoh soal, sebagai contoh misalkan ya di sini. Ini adalah polarizing sheet ya, ada dua sama-sama vertikal kan ya. Satu ini vertikal ke sana, ini ke sana. Jadi dia masih kelihatan di tengah. Tapi kalau itu kita putar, ini ya tidak kelihatan. Oke? Jadi artinya ada cahaya yang tidak diteruskan gitu ya. Jadi artinya ini totally apa istilahnya? Jadi yang di sini itu terpolarisasi secara penuh ya. Vertikal, ketika saya putar jadi tidak terlihat. Jadi dia benar-benar hilang. Oke, ini sebagai contoh misalkan ya di ini gambarnya seperti ini. Jadi awalnya dia tidak terpolarisasi, kemudian itu vertikal, jadi terpolarisasi gitu ya. Kemudian dia itu ini yang pertama, yang keduanya itu kita lembar polarisasinya itu kita putar sekitar 60 derajat dari sumbu vertikal. Kemudian yang ketiganya itu kita putar 30 derajat dari awal, dari sumbu awal. Oke? Nah, jadi dari dia itu tidak terpolarisasi, jadi terpolarisasi vertikal. Oke? Ketika terpolarisasi vertikal, saya putar ininya 60 derajat, dia jadi seperti ini. Oke? Nah, kemudian kalau saya putar lagi 30 derajat dari sini terhadap sumbu yang vertikal, bukan vertikal, yang sudutnya 60 derajat ya dari sini, ya itu jadi seperti horizontal begini, maka nanti akan saya dapatkan cuma horizontal aja yang lolos gitu. Oke. Nah, jadi kalau saya dapatkan, saya rumuskan di sini. Jadi kalau yang pertama ya dari lembar pertama yang terpolarisasi, I1 itu adalah setengah I0. Oke. Kalau lembar kedua itu adalah I2 sama dengan I1 cos kuadrat 60 derajat. Oke. Karena kan ini saya putar 60 derajat. Kemudian kalau saya putar lagi 30 derajat, ya berarti I3 itu sama dengan I2 cos kuadrat 30 derajat. Jadi kalau I2 ini saya masukkan dari sini, itu akan saya dapatkan rumus seperti ini. Jadi I3 itu sama dengan setengah I0 cos kuadrat 60 dikali dengan cos kuadrat 30 didapatkan I3 dibagi I0 sama dengan 0,094. Nah, pertanyaannya sekarang bagaimana kalau 60 derajat ini saya langsung apa istilahnya? Saya langsung buat sudutnya 90 derajat. Artinya tidak perlu bertahap seperti ini. Yang terjadi apa? Yang terjadi apa? Halo? Halo, halo. Nicholas, Aryanda.
Kalau misalkan gimana tadi, Pak?
Ya, kalau misalkan yang lembar kedua ini, lembar polarisasi kedua ini sudutnya jadi 90 derajat, langsung aja horizontal.
90 derajat berarti?
Ya.
Oke.
Jadinya gimana itu?
Apa dia langsung berubah 90 derajat polarized-nya?
Maksudnya ada cahaya yang lolos nggak? Cahaya yang lolosnya polarisasi seperti apa?
Kalau misalkan itu langsung 90 derajat gitu, Pak, nggak?
Iya. Kalau ini
Oh,
kan ada dua nih.
kalau gitu nggak ada yang nembus, Pak.
Ya, tidak ada yang nembus ya, karena kan tadi kan cos mana tadi? Sudut ini nih cos kuadrat theta ya, kalau tetanya 90 dia 0. Oke? Jelas ya?
Jelas, Pak.
Oke. Kemudian kita juga belajar tentang pemantulan dan pembiasan. Ini sebagai contohnya, mana tadi? Ya, ini adalah cahaya datang, pantul dengan dibiaskan. Ini contohnya ya. Ini misalkan dari udara ke air ya. Ini datang, kemudian dipantulkan, ini sama kan theta 1 dengan theta prime yang dikatakan hukum pantulan, hukum pemantulan ya. Kemudian ini ada namanya pembiasan, cahaya yang dibiaskan. Dan cahaya yang dibiaskan itu memenuhi hukum Snellius, ya. Hukum Snell, Snell's law. Oke, ini adalah hukum refleksi, hukum pemantulan, ini hukum pembiasan. Oke. Ini contoh beberapa medium ya, indeks bias. Nanti contohnya misalkan antara cahaya datang dengan cahaya yang dibiaskan itu sama-sama indeks biasnya sama, N1 dengan N2-nya. Oke, maka dia akan seperti ini. Jadi langsung diteruskan. Ketika dia itu misalkan N2 itu lebih besar pada N1, misalkan ini adalah yang N1 itu adalah air, yang N2 itu adalah kaca atau air, maka didapatkan sudut biasnya itu akan menuju ke garis normal ya, atau sumbu normal. Kemudian kalau dia itu dari kaca ke udara, ya, sudut pantulnya itu kecenderungannya akan menjauhi dari garis normal. Itu fenomena yang diamati. Nah ini kemudian disebut ada namanya dispersi kromatik. Jadi N itu sendiri secara umum itu tidak konstan sebenarnya, bergantung pada suhu atau temperatur dan juga di sini bergantung pada lambdanya seperti apa. Jadi itu tidak konstan. Itu dikatakan bahwa bahan tersebut itu punya dispersi kromatik. Nah itu artinya apa? Jadi kalau kita lihat, misalkan ini dari udara ke kaca ya, itu kita bisa lihat bahwa kalau untuk misalkan ini adalah cahaya putih. Cahaya putih itu adalah gabungan dari berbagai cahaya, ya, dari merah sampai biru. Nah, jadi kalau dia itu memasuki kaca misalkan, yang N2-nya lebih besar daripada N1, itu yang terjadi adalah cahaya biru, ini akan terpisah tentunya. Cahaya putih itu akan terjadi pemisahan antara cahaya biru dipisahkan dengan merah gitu ya. Nah, cahaya biru itu kecenderungannya sudut biasnya mendekati garis normal. Sedangkan sudut merah, sudut merah itu dia cenderung menjauhi, lebih besar. Nah, kebalikannya kalau dia itu mulai dari kaca ke udara, gitu ya. Kaca ke udara itu justru yang biru itu kecenderungan sudut biasnya itu lebih besar dibanding dengan sudut yang cahaya merahnya. Gitu. Nah, ini contohnya, jadi kalau ada prisma misalkan ya, Anda sinari dengan cahaya putih itu akan terurai jadi beberapa spektrum. Jadi kita bisa tahu bahwa sebenarnya cahaya putih itu merupakan gabungan dari cahaya-cahaya seperti merah sampai biru. Nah, ini contohnya misalkan Anda bisa, kalau ada matahari ya, ada prisma gitu ya, Anda bisa lihat di situ ternyata di layarnya misalkan di tembok itu ada ada pemisahan cahaya. Oke, mungkin dari saya itu aja. Mungkin ini nanti kita bahas minggu-minggu depan ya, terkait dengan ini. Ada pertanyaan nggak? Pertanyaan? Kalau tidak ada, saya akhiri ya. Terima kasih semua. Selamat siang dan jaga kesehatan.
Terima kasih, Pak.
Ya.